Okay, say we want to do a statistical test and we want to use Excel to do it. And in particular, we're going to look at the two-sample t-test. We'll use this spreadsheet to look at how t-tests can be used to compare the means of samples to determine whether the means of the populations they come from are likely to be different. So in this spreadsheet, we can see we have two data sets, set A, which has 9 values, and set B, which has 9 values. These are samples from populations. We can see that set A, as plotted over here, tends to have slightly larger values than set B, which is indicated by the red or the orange. But again, these are the samples, so we don't know whether the populations also have different means or not. That's the purpose of these t-tests. The first thing we'll do is we'll use Excel to compute the means of each of these samples. To do this, we'll use this function in Excel called average. So the way this works is, in this cell, we're going to type in an equal. That tells Excel to perform a calculation and return the result instead of just accepting a number into that cell. Then the function name, average, which tells Excel which function we want it to do. And then in parentheses, we indicate which area we want it to go get the numbers from that it's going to use for its function. We can see that the mean for data set A is given here, and that's going to be 10. The mean for data set B is given here, and that's going to be 8. Next, we want to compute the standard deviations. For the standard deviations, what we're going to do is use this function stdev for standard deviation, .s because this data is a sample, C3 through C11 because that's the area where the data values for set A are that we want to calculate the standard deviation for. When we're finished with this, the function returns the value of 1.8708. And when we do the same thing for data set B, that returns the value of 1.5. The means are useful for interpreting any results we get from our t-test, and the standard deviations are useful descriptive statistics to help us understand the variation in our data. We do need to calculate two other values before we proceed. These are the degrees of freedom values that we'll use for our tests. The first equation is for the heteroskedastic test, and there's a very long equation that we won't go into the details of here, but you can watch the other video on this channel about the introduction to the t-test technique to learn about where this comes from. In any case, you can see this equation here uses a bunch of the other values to get a degrees of freedom value. For the homoscedastic test, it's much easier. It's just the total number of data values minus 2, and we use the count function to tell us how many values are in the region that we have selected. Now we're ready to go ahead and do our t-tests. So let's go to the Excel sheet, look at the homoscedastic t-test. In cell F4, we have the following equation. T-test, because that's what's being done. C3 through C11, that's one set of data. D3 through D11, that's another set of data. 2, because we're doing a two-tailed test. And then this last 2 is telling Excel that we want to do a homoscedastic test. Once all this is entered, then we just hit enter, and it returns the p-value of that homoscedastic t-test. If we want to figure out the t-value that goes with this p-value, we need to use the following equation. T inverse, and it's two-tailed. F4 is the p-value that we're looking at, and then C16 is the degrees of freedom value down here for our homoscedastic t-test. When we use this T inverse function using the p-value, the value that's returned is the t-value that we would get when we're doing this homoscedastic t-test. It's a little awkward, but it's because Excel doesn't do this automatically, and because most people are much more concerned about the p-value of a t-test instead of the t-value anyway. Interpreting the results of our t-test for the homoscedastic test, we see that the p-value of 0.0236 indicates that the populations that these samples come from are unlikely to have the same mean. In fact, there's only a 2% chance that our samples would be this different if the populations had the same mean, so we would conclude that they have different means. That's what that p-value of 0.0236 indicates. Moving on to our heteroskedastic t-test, we have a very, very similar equation here. The only difference, in fact, is that there's a 3 instead of a 2 to indicate to Excel that we wanted to do a heteroskedastic test instead of a homoscedastic test. Our p-value we can see is 0.0242, almost exactly the same as the homoscedastic test. We use the same equation here, the T inverse equation, two-tailed, now using the p-value for our heteroskedastic test, and using the degrees of freedom in C15 that's this cell here with the more complicated value. You can see the fewer degrees of freedom, it's about 15 instead of 16. That smaller number of degrees of freedom gives our heteroskedastic test a little bit less power, which is why that p-value is a little bit larger, even though the difference in means and the standard deviation is the same for our two data sets. Our t-value is also a little bit larger, but our reduced degrees of freedom results in a not as significant p-value. Moving on now to our paired t-test, we have, again, a very similar equation, the difference being the 1 at the end here to tell Excel to do a paired test instead of an unpaired test. The p-value is 0.0736, so in this case, we can see that the differences in these sample means would not be significant, and that's because although there's a difference in the means and standard deviation, the pattern of differences is not consistent when you pair up the values. So for example, although dataset B is usually smaller than dataset A, this third pair of values, you can actually see the inverse has occurred, and that's basically what's causing there to be not a consistent pattern of the pairs of values that would lead a statistical test to conclude a smaller mean for dataset B compared to dataset A, or really the populations that they're from. Same equation here, using the t inverse if we wanted to get the p-value. The difference here is now, instead of using a more complicated degrees of freedom, we can just use the degrees of freedom of that paired test, which is the number of values minus 1. We can see that smaller t-value, which is what we would have expected to match up with that larger p-value. Let's look at an interesting example of how this paired t-test works. So in this case, we had a non-significant result. But if we just switch two of the values, so values 3 and 4, which I've indicated here, if we switch them, the same values, right? So all the summary statistics are exactly the same. But if we switch them in a way that they're more consistent in terms of this one being lower and the fourth one being higher in the same way that the third and fourth for dataset A are higher, you can see that now the t-value for the paired t-test gets much larger, and the p-value actually becomes more significant than either of the unpaired tests. We can see how the paired test really does use the correspondence between each pair of values, not the overall summary statistics themselves. Another interesting example, if we go back to our starting values, is to look here. All I've done is I've raised the values of dataset B by 1. Each of the values is larger by 1, so the mean has gone up, but the standard deviation has stayed the same. Same exact equations in these cells, calculating these values, and we can see now that the t-values are all much smaller because there's less of a difference between these two samples, and now the p-values are larger, indicating that there is no longer a significant difference between the means of these samples because they're very close together. This totally makes sense, because if the values are not as different, we expect the difference between them to be less significant. Let's look at another example. So this is our starting data set. What I've done here is I've just increased the variance of dataset A. The mean is the same, but now the standard deviation is larger. You can see the effect it has on the degrees of freedom, reducing them from 15 down to about 12, really 11 because we tend to round downwards. And now, just with the increased variance, now again, these p-values for the t-tests are no longer significant. So even though the means in the samples are as different as they were before, 10 versus 8, the increased variance in dataset A has caused us to have non-significant differences between our two samples. So Excel can be used to easily calculate t-test values. The p-values are incredibly easy, just with this equation. If you want the t-values themselves, you have to use this inverse t function, which is a little bit more complicated, but again, it's not that bad, and the function is built into Excel automatically. And we can look at the spreadsheet and we can see the effect of the pattern in terms of pairing, how the difference in the means is important, and how the magnitude of the variances, or standard deviations, are important. Let's look at a second data set. So here we have 8 values in each of these two sets. The means, the standard deviations, and the degrees of freedom are calculated here. Means the same way, using the average, using the stdev.s function, using this longer equation, but now instead of 9s and 81s and 8s, it uses 8s and 64s and 7s. And again, that's an equation that's explained in one of the other videos on this channel. And then the homoscedastic test degrees of freedom can see selects this area and subtracts 2. Now Excel, when it selects empty cells, like you can see here, it will ignore them as long as there's nothing in them. So it's actually treating those empty cells as if they don't even exist. That also works if you're calculating averages or standard deviations or anything like that. Moving on to our first homoscedastic t-test. In this cell, we can type it out now, equals, because it's an equation, t-test, and then in parentheses, we're going to select our first set of data, comma, second set of data, comma, 2, because we're interested in a two-tailed test, comma, 2, because we're interested in the homoscedastic test right there. That gives us this p-value of 0.0425. So we have a significant difference. But if we wanted the t-value as well, we would want to type in the t-inverse equation. So t dot inverse dot 2 tails. And then in our parentheses, we're going to select the probability value, which is actually our p-value, and then comma, the degrees of freedom for the homoscedastic test. That's down here in this cell C16. So we click on that, close parentheses, and return. So our t-test value is 2.2315. Now for the heteroskedastic test, again, equals t-test, parentheses, first set of data, comma, second set of data, comma, 2 for 2 tails, comma, 3 for heteroskedastic test, 0.0448. Again, not quite as significant as the homoscedastic test, and that's because the degrees of freedom are lower, right? They're 12.4 instead of 14. Now to get our t-value, t dot inverse dot 2 tails, and then our probability is our p-value, degrees of freedom down here, 2.2398. Now for our paired t-test, equals t-test, first set of data, comma, second set of data, comma, 2 tails, comma, 1 for paired t-test. For our t-value, t inverse, 2 tails, probability. Then the degrees of freedom is count the number of values, and then we can subtract 1. That's the degrees of freedom for our test, 2.5026. So a larger t-value and a slightly smaller p-value for our paired test with this data. This shows all the equations that we used in our 2 spreadsheets that we just went through. The Stats Examples website has a PDF of this screen and a downloadable Excel file that you can use. You can find other videos about statistics on the Stats Examples website or by looking at the other videos on this channel.